Remember all those little half-truths that we always have to correct somewhere along the way? Well, you'd think we'd be done with that by now, but no, sorry. You know when we were doing some energy questions before, and we would calculate the delta H, and then we'd say, well, how much ice can you melt with the heat provided from this reaction, or something like that. And we always try to calculate by taking the amount of heat released in the delta H, how much ice we can melt, and things like that. Well, you know what? The amount of heat that comes off of an exothermic reaction, not all of that heat is going to actually be able to do useful work for us. Always, some heat in a reaction must be donated in order to increase the entropy of the molecules and increase the entropy of the universe. So, really, you cannot get all the energy off of a reaction and directly apply it to a job. We're always losing energy somewhere. That's why you can never make a perpetual motion machine. It can't happen. Entropy must actually take some of that energy. And so, the first law of thermodynamics says, you can't come ahead in terms of energy, you can only break even. And then the second law of thermodynamics says, no, you can't even break even, sorry. So look, Gibbs comes up with his calculation to determine how much free energy can come off of a system. If you take the delta H of a reaction and then take away a certain amount of energy that's going to be applied to entropy, then you'll get an amount of energy that can be used for useful work. That's called Gibbs free energy. So his free energy, the amount that's freed up to do useful work, that's his calculation. Now why is this going to be useful? Because in this equation, whenever you get a negative value for delta G, a reaction is spontaneous. Negative delta G, spontaneous reaction. So if we know the delta H for a reaction, and we know the delta S, and scientists have actually given us charts, and you probably have a data table in the back of your textbook that has delta S values. By the way, when you don't write down anything after delta S, it's system. So you look up the system values for something, for a molecule, and then you can actually arrive at whether, and an equation, delta S for a molecule or an equation, you can arrive at whether a reaction is actually spontaneous or not. Let's look at one. Okay, so here it is. You've got water solid turning into water liquid. You want to know if that is spontaneous at a temperature of minus 10 degrees Celsius. You know that already. Of course not. Water doesn't melt at minus 10. No. So here's the thing. We can actually prove that with some numbers and a formula too. Now, the delta H for this reaction is 6.03 kilojoules per mole of water solid turning into water liquid. Also, I'm going to tell you that the delta S for this is not something you can necessarily just look up, but you can see here that the delta S is 22.1 joules per Kelvin mole. Look at that. Entropy actually has a value as a unit. It's joules per Kelvin. Delta H divided by T, joules per Kelvin per mole. Okay, so I give you those values and say, is it spontaneous at minus 10? Plug it into the formula, Gibbs free energy formula, and this is what you get. Delta G equals the delta H here, but you got to turn it into joules, which is what I did, in order for it to be able to add to, or be subtracted from, or have subtracted from it a joules unit as well. Okay, so make sure you do that. Be very careful of that. All the units are the same. Then the delta S value goes into here, but the temperature has to be converted to kelvins because this unit's in kelvins and it has to be in kelvins, and you know what? It just makes perfectly good sense. If you had 0 degrees Celsius, 0, then 0 here, if you put it in for temperature, times the delta S would just blow it away and give you nothing. But that's not good. You can't have that. The only time that you have absolutely no entropy in a system is at 0 K. 0 kelvins, which is negative 273, which is absolute zero, right? That's when all motion of everything stops. It's a theoretical point. We can't get to it yet. So here's the thing. The temperature has to be in kelvins. By the way, the entropy of a perfect crystal at 0 K is 0. That's the third law of thermodynamics. Cool. Now, when you do the math, you get the delta G equal to positive 217 joules per mole. But here's the thing that you're really interested in. the positive. Positive means non-spontaneous. So, this reaction is non-spontaneous at 10 degrees because the delta G is a positive value. Cool. You know, if you substituted 273K in here, that's actually 0 degrees Celsius. And this delta G would be 0. Because right at the phase change, a delta G value is always 0. And then, if you have 10 degrees Celsius here, that would be 283, and then this number would actually work out to be a negative. Because at 10 degrees Celsius, ice will melt, and that would be spontaneous with a negative delta G.